in the previous videos, we demonstrated that you could take, microscopic models that describe the physics of molecules, and you could apply the calculus of thermodynamics in order to relate them to macroscopic measurables, relate them to things like pressure, volume, and temperature. Right? And so that's one aspect of utility for the calculus of thermodynamics. But even if you don't have some sort of molecular model, you could still apply the principles of the calculus of thermodynamics in order to gain insight about a physical system. Okay? So if you don't have a molecular model, you can still apply calculus of thermodynamics to gain insight. Okay? And so in the in-class problems for Chapter 6, I'm going to demonstrate to you various examples of how you could use the calculus of thermodynamics in order to develop equations for temperature, pressure, and volume, just from, starting from the basics. And during these videos, there's essentially three, sort of mathematical tools that we're going to go back to quite a bit in order to help us develop our models. All right? And so these are three main important, principles of partial derivatives that we're going to use. So manipulate. All right? And so essentially, if you want to manipulate some sort of function theta, all right, where theta can be, internal energy, entropy, enthalpy, the Helmholtz function, Gibbs function, or even temperature, pressure, and volume. And so just to make sure, this little epsilon is just a math way of saying is one of these things. All right? So if you have, a function that's one of those things, here's three common mathematical tools that you'll want to use when you're trying to use the calculus of thermodynamics in order to develop a model. Right? So the first mathematical tool that we'll go to quite a bit is the expansion rule. Okay? And so, let's say you have, or you want to derive some sort of partial derivative, some partial derivative of theta with respect to u. That u is not internal energy. This u is just a random variable. All right. So partial derivative of theta with respect to u at constant v, which is also just a random variable. Okay. So let's say you want a partial derivative in that form. But when you defined theta originally, you had it in terms of some other variables. Okay. So let's say x and y were your canonical variables. And as a result, the total derivative of theta was in this form, right? Okay. Or maybe to make it more clear, the total derivative was in this form. Constant y, and then the one for y. Okay? All right, so that's what we've seen before. Okay? And so if you want to get this derivative, this sort of derivative, what you would want to do is you would want to apply the expansion rule. Okay? du v plus d theta dy dy du constant v. All right. So as you remember, that's just the form of the expansion rule. And the utility of applying the expansion rule in this situation is that from your total derivative of theta, if we call this alpha and we call this beta, you would know what these things are. And so when you apply the expansion rule, this alpha and beta would also be there. All right? And so this helps. Basically, the reason to use the expansion rule, as we've talked about before, is it's a way to introduce new variables into your function. Okay? And so that's the utility of using the expansion rule. And so in the end, our partial derivative would look like this. dx du constant v and beta dy du constant v. All right? And so that's the sort of general form of the expansion rule. Okay? The next tool that we'll use quite a bit is the triple product rule. So triple product rule. And so here, let's say you had a partial derivative in this form where, for instance, theta is some unmeasurable property. So like an enthalpy, internal energy, entropy. All right? And so if you needed, a partial derivative in this format, or if you have a partial derivative in that format, one useful tool that you could apply is the triple product rule, where this partial derivative expands into this form. Okay. Where the theta on the left-hand side, even though it's being held constant here, on the right-hand side, it ends up being in the numerator of the partial derivative. Okay? All right? And so this is useful if you just kind of want to rearrange the order of the variables in your partial derivative. And so we'll also use this tool in our derivations. The last mathematical tool we'll use quite a bit is the Maxwell relation, or Maxwell relations. Okay? And I just want to remind you about, in the previous videos, we had a partial derivative in this format, where I pointed out that if you look here at S and T, those both belong to the same conjugate pair. They were the thermal conjugate pair, right? And P and T here, we also saw that these were the canonical variables for the Gibbs energy. Okay? All right, and so if you have anything in this sort of form where the numerator of the partial derivative and the constant variable belong to the same conjugate pair, and the denominator of the partial derivative and the constant variable both belong to the same, or are both canonical variables to some sort of energy function, that tells you that you need to apply the Maxwell relations. Okay? And so the Maxwell relations invoke the commutative property of the second mixed partial derivatives. Okay? And so all that is saying is that if you take the partial derivative of theta with respect to x and then do it again with respect to y, should be a second here, the order that you take those partial derivatives does not matter. Okay? Okay? And this can be useful because in some cases we may know what these things are. These are, not air. Okay? And so this helps us relate different sort of variables to one another. Okay? All right, and so the expansion rule, the triple product rule, and the Maxwell relations, essentially these tools make up the backbone of the calculus of thermodynamics. And we're going to use these tools in order to help derive mathematical models that describe our system.